Okay, this is the video for 5.1 on trigonometric identities. So we started class by making a foldable to help us with all of our trigonometric identities. So if you are absent, I'm going to run through the steps on how we made that real quick. So we took 3 strips of different colored paper and we stacked the sheets and staggered them about an inch each, so that each tab is going to be about the same amount. And then we folded the top down, so then we have 6 tabs, and I put 2 staples at the top. So the very first one is just going to be the name, trigonometric identities, and then we have a tab for each of the different type identities that we're going to look at. So the first set of identities are the reciprocal identities, and we learned these in chapter 4 before Christmas, that the sine of an angle is equal to 1 over the cosecant, cosine of an angle is equal to 1 over secant, tangent is equal to 1 over cotangent, cosecant is equal to 1 over sine, secant is equal to 1 over cosine, and cotangent is equal to 1 over tangent. So when something is a reciprocal of something else, you can take that number and just flip it over, or you can do 1 divided by that number. That means the same thing. Flipping it or 1 divided by that number will get you the same answer. The next set of identities are the quotient identities. So the quotient identities are that the tangent of some angle equals sine divided by cosine. And since we know that cotangent is the reciprocal of tangent, then you just flip that over. Cotangent is equal to cosine over sine. Next are the Pythagorean identities. And we'll talk about where these come from later on. But sine squared plus cosine squared is equal to 1. Tangent squared plus 1 is equal to secant squared. And cotangent squared plus 1 equals cosine squared. You can take any of these Pythagorean identities and rearrange them if you want to solve for one of the functions, and it still equals the Pythagorean identity. So just rearranging in the equation doesn't change it. Okay, so these next ones are called cofunctions, and angles that are cofunction angles are actually complementary angles. When you see pi over 2, remember that pi over 2 is equal to 90 degrees. So two angles that add to equal to 90 degrees are called cofunctions. And any angles that are cofunctions, their sine and cosine value would be equal to each other, and any of those that are listed on here. So if I looked up, for example, the sine of 30 degrees, it's going to be equal to the cosine of 60 degrees, its complementary angle, and vice versa. Any two angles that add to equal 90 degrees or pi over 2, these two trig values would be equal to each other. So a lot of times it's difficult to understand that concept. So for now, if you just memorize these cofunction identities and know that anytime you see a trig function with pi over 2 minus theta, that's probably going to be an identity that you're going to substitute one in for the other. The last identities are the even-odd identities, and these are for angles that are positive and negative angles and how they relate to their trig values. So the first one, for example, says that sine of negative theta is equal to the negative sine of theta. What that's talking about is if I found out the sine of 30 degrees and the sine of negative 30 degrees, those answers are actually going to be opposite. So it's saying that the sine of a negative angle is equal to the opposite of the sine of the positive angle. Okay, so there's 4 of these trig functions that is true, that their answers are opposite, and then there are 2 trig functions that their answers are the same. So, for example, cosine of a negative angle is actually equal to the cosine of the positive angle. Same thing for secant. Okay, so those are the 2 even identities and the rest are odd identities. Okay, so now we're going to look at the examples for this section, and some should be similar to what we did before in Chapter 4, and maybe that'll help some of you that are struggling a little bit. So example 1 says, if the cotangent of x is equal to 2 over 5 square root of 5, and the sine of x is equal to the square root of 5 over 3, find the cosine of x. Okay, before, in Chapter 4, most of the time we probably would have drawn a triangle and labeled the parts of the triangle and then found the missing pieces. And you can still do that on this problem, but I'm going to show you how you can use the identities that we have in our flip book to help us find what we're looking for here. So we are given cotangent and sine, and I'm trying to find the cosine value. Well, one of the reciprocal identities is that cotangent is equal to cosine divided by sine. And in this case, I've been given the cotangent and I've been given the sine. I'm trying to find cosine. So I'm going to plug in the values that I know into this equation and then solve for what I'm looking for, which is cosine of x. So 2 divided by 5 square root of 5 is equal to cosine x divided by square root of 5 over 3. So since I'm trying to solve for cosine, then I'm going to multiply by what's being divided by. So on both sides, I'm going to multiply by the square root of 5 over 3. On the right-hand side, that's going to cancel. That's why I multiplied on both sides. On the left-hand side, I want to simplify before I actually multiply because I see that the square root of 5s are going to cancel each other out. And then I'll be left with 2 over 3 times 5, which will be 2 over 15. Okay, so I found the cosine of x using those trig identities. You could have drawn a triangle, labeled the parts, opposite, adjacent, and hypotenuse, plugged in the information they gave you, and you still would have gotten the same thing. Okay, example 2 says if tangent of theta is equal to -8 and the sine of theta is greater than 0, find the sine and the cosine. So in this case, the information that sine is greater than 0 tells me that the sine value is positive and the negative value is, the tangent was the negative value. So the reason this helps me is I need to know what quadrant this triangle is in to be able to get the correct sign, positive or negative, on my answers. So remember, before Christmas, we had this picture that said, all students talk constantly, or all students take calculus. And what this represents is where the A is in quadrant 1, all trig functions are positive. In quadrant 2, only sine and its reciprocal are positive. Quadrant 3, only tangent and its reciprocal. And then in quadrant 4, only cosine is positive. So this helps me because I'm looking for the quadrant where tangent is negative but sine is positive. So the only place that sine is positive and tangent would be negative is in quadrant 2. So that's where this triangle would have to be drawn if I was going to solve it this way. So just being given that the tangent is -8 isn't enough for me to plug that into the triangle to find the missing pieces. So I'm going to use a different reciprocal. I don't have, or a different identity. I don't have an identity that directly relates tangent to sine or tangent to cosine. It does for both of them, but since I'm solving for both, that doesn't help me. So I want to use this identity, which is one of the Pythagorean identities, that says that tangent squared plus 1 is equal to secant squared. So I'm going to plug in a -8 for tangent and then square it plus 1, and that's going to equal secant squared. Okay, so if I do -8 squared plus 1, that's going to be 65. That gives me secant squared. So I need secant. I'm going to take the square root of both sides. And remember, when you take the square root of something, it's going to be the positive and negative square root of that value. So since I know the secant, then I actually know the cosine value because cosine is the reciprocal of secant. So I can do 1 over the positive and negative square root of 65. Now I can't leave the square root of 65 in the denominator, so I have to multiply by the square root of 65 on the top and bottom, and this will actually be the square root of 65 over 65. I've gone ahead and dropped the positive sign because I know in quadrant 2 only signs should be positive, so that means my cosine answer has to be negative. Okay, so now that I know that cosine is negative square root of 65 over 65, I can use the quotient identity and plug in tangent and cosine and solve for the sine value. So, negative 8 is equal to sine theta over negative square root 65 over 65. And like the last problem, I would multiply by negative square root of 65 over 65 on both sides. And the sine would equal positive 8 times the square root of 65 over 65. Okay, example 3 says if tangent of theta equals 1.28, find the cotangent of pi minus or theta minus pi over 2. Anytime you see something in parentheses with a theta and a pi over 2, you're probably going to use the cofunction identities. But the cofunction identity actually is switched around, and it's pi over 2 minus theta. So if I'm going to move the pi over 2 and the theta and switch places, then I actually have to change the sign. So that's what this negative out in front of the parenthesis is. If I switch places with those two, then I'm going to factor a negative out front. So that's why I've put the negative there. Okay, then I'm going to use the even-odd identities. If I kind of ignore what's in parentheses here, and I just say that this is the cotangent of negative something, doesn't matter what that is in the parenthesis, I look at the even-odd identities, and it tells me that that is equal to the negative cotangent of whatever the angle is. So I can substitute and write negative cotangent of pi over 2 minus theta. Okay, so that was using the even-odd identities. Now going back to the cofunction identities, cotangent of pi over 2 minus theta is actually equal to tangent. So I substitute cotangent of pi over 2 minus theta for tangent. Well, they gave me what the tangent value is equal to. It is 1.28. So that means that this angle is actually equal to negative 1.28. Okay, example 4. We are going to simplify the secant x minus tangent x times sine x. These last two problems are going to be very similar in that we're simplifying a trigonometric expression. And anytime you're simplifying these expressions, you need to try to get each of the terms into sines and cosines if possible. Okay, so we're going to use those basic trig identities, the reciprocals, the quotient identities to start with. Okay, anytime you can get it down to sines and cosines, that's what you're trying to do. Now, sometimes it seems like it gets messy for a while, and then all of a sudden things start to cancel out and things look a lot nicer and neater, and that's what it means by simplify. So I'm going to start by replacing secant x with 1 over cosine x. And then minus, I'm going to change tangent x to sine x over cosine x. And then I'm going to leave sine x like it is, and I went ahead and put it over 1. Okay, so when you're multiplying fractions, remember you multiply the tops and multiply the bottoms. So this is going to be 1 over cosine x minus sine times sine is sine squared x over cosine x. Now remember, in order to add or subtract fractions, they have to have a common denominator. And in this case, they do. Cosine x is a common denominator. So that means I can smush these fractions together, and it will be 1 minus sine squared over cosine. Okay, now I'm going to go over here and do some work in the cloud off to the side. Anytime you see some type of trig function squared, you're probably going to use one of the Pythagorean identities. And I'm going to use the first one, sine squared plus cosine squared equals 1. Now to be able to help me out for this problem, I want to rearrange this Pythagorean identity so that I could substitute something in for 1 minus sine squared x. So if I rearrange this Pythagorean identity and I subtract sine squared on both sides, this will leave me with cosine squared x equals 1 minus sine squared. So that means anytime I see a 1 minus sine squared, I could replace it with cosine squared x. So that's what I'm going to do back in the problem. On the top, I'm going to put sine or cosine squared x over cosine x. And cosine squared x is the same as cosine times cosine, so it's going to cancel with one of the cosines that would be on the bottom, and we would just be left with cosine x. So all of that expression that we started with at the very beginning, once we go through and use these identities and substitute one in for the other and then use a little bit of algebraic skills, it all simplifies and equals cosine. Okay, one more, example 5. Same process. We have cosecant theta times secant theta minus cotangent theta. So always try to get it in terms of sines or cosines if possible. So I know that cosecant is equal to 1 over sine, secant is 1 over cosine, and cotangent is cosine over sine. So I'm going to multiply those first two fractions. When you multiply the top, 1 times 1 is just 1. On the bottom, sine times cosine is just sine times cosine. It's like if there were two different variables. And then minus cosine over sine. Now just like before, in order to add or subtract fractions, they have to have a common denominator. And the common denominator in this case would be sine times cosine. The second fraction does not have a cosine, so I need to multiply by cosine on the top and bottom. So the first fraction is going to stay the same, but the second fraction becomes cosine squared over sine times cosine. Now that they have the same denominator, I can smush them together and subtract the tops. So it would be 1 minus cosine squared over sine times cosine. Now I'm going to go back to the cloud to one of those Pythagorean identities, and this time I want to rearrange it so it helps me for this problem. So if I rearrange and subtract the cosine on both sides, then sine squared equals 1 minus cosine squared. Remember, rearranging doesn't change the identity, it's just another form of it. So back in our problem, I can replace 1 minus cosine squared with sine squared. And on the bottom, I still have sine theta times cosine theta. Now that cosine, or the sine that's on the bottom, is going to cancel with one of the sines that's on the top. So I would be left with sine over cosine. And since I can simplify this further and get this down into one term or one trig function, this is the same as equaling tangent. So the goal is normally to get it in terms of sines or cosines, but if you can simplify it down to one other trig function, then go ahead and do that.